Imagine a vending machine. You can only put in certain coins, like a 10-rupee note or a coin, and it will only give you back certain snacks. A function works the same way. The set of all the inputs you are allowed to feed into the function is called the domain. The set of all the outputs the function can possibly spit out is called the range. So if you think of a function as a machine that takes a number and does something to it, the domain is the menu of numbers you can safely put in without breaking the machine, and the range is the menu of snacks you might get back. Why do we even care about domain and range? Because if you try to put an illegal input into a function, the whole thing crashes, you get an undefined result, which is useless in math. For example, you can't divide by 0, and you can't take the square root of a negative number in the real number system. Knowing the domain tells you exactly where a function is safe to use. Knowing the range tells you what values the function can ever reach, which is like knowing the highest and lowest points on a roller coaster. In calculus, we constantly ask questions like where is this function continuous, or so what are its maximum and minimum values? And you can't answer those without first understanding the domain and range. To find a function's domain, we always start with the biggest possible set, all real numbers. Then we act like detectives and remove any input that causes a math crime. The two most common crimes are dividing by 0, and taking an even root, like a square root or a fourth root, of a negative number. So for a function like 1 over the quantity x minus 2, we say x minus 2 cannot be 0, which means x cannot be 2. The domain is all real numbers except 2. For the range, we look at the outputs the function can produce when we feed in every number from the domain. Sometimes you can see it from a graph, the y values the graph actually covers. Other times you solve for x in terms of y and see what y values are possible. For our example, 1 over x minus 2, the output can be any real number except 0, because a fraction like that is never 0. Let's solve a concrete problem. Imagine you throw a ball straight up. Its height above the ground in meters after t seconds is given by the function h of t equals 20t minus 5t squared. What are the domain and range for this real-world situation? First, the domain. Time t cannot be negative, we start the clock at the moment of the throw, so t is greater than or equal to 0. The ball hits the ground when the height is 0 again. We solve 20t minus 5t squared equals 0. Factor out 5t to get 5t times the quantity 4 minus t equals 0. This gives t equals 0, the start, and t equals 4, when it lands. So the domain is t between 0 and 4 seconds, inclusive. Now the range. The height starts at 0, goes up, and comes back to 0. The maximum height happens exactly halfway, at t equals 2 seconds, because a parabola is symmetric. Imagine a juicer. You put an orange in, and orange juice comes out. A function works the same way. We give it a name, often a single letter like f. You feed it an input, which we usually call x. The function does its job and produces exactly one output. We write this output as f of x, with the input in parentheses. The parentheses don't mean multiplication here. They are like the slot where you drop the input in. So f of x is just a short way of saying the output you get when you put x into the machine named f. Without a name, a rule like add 3 is just a sentence. Giving it a name, like f, lets us talk about it precisely. The notation f of x shows the relationship clearly, the output depends on the input. More importantly, it lets us ask what happens at a specific input. We can evaluate the function at any number in its domain. This idea of plugging in a value and getting an output is the very first step in drawing graphs, finding slopes, and everything else in calculus. It turns a vague rule into a tool we can use. Evaluating a function is like following a recipe. The expression after the equal sign tells you what to do with x. To find f of 2, you literally replace every x you see with the number 2. If the input is more than just a number, like a plus h, you must put the whole input in parentheses. This is a common mistake. So f of a plus h means you substitute the entire quantity for plus h wherever you see x. Then you simplify using the normal order of operations, parentheses first, then exponents, then multiplication and division, and finally addition and subtraction. The result is always a single real number, as long as the input is in the domain. Let's see this in action. A rock is dropped from a 20-meter cliff. Physics tells us its height above ground after t seconds is given by the function h of t equals 20 minus 5t squared. The domain here is t from 0 to 2 seconds, because after that it hits the ground. Let's find its height at exactly 1 second. We evaluate h of 1. This means we replace t with 1 in the formula. We get 20 minus 5 times 1 squared. 1 squared is 1, times 5 is 5. 20 minus 5 is 15. So the rock is 15 meters above the ground at the 1 second mark. The same method works for any time, just plug it in and simplify. We already know a function is like a machine. You feed it an input, it gives back exactly one output. But not all machines work the same way. Some double the input, some square it, some keep it the same. These different rules are what we call types of functions. We give each type a name based on the pattern it follows, like linear for a straight line rule, or quadratic for a squaring rule. Think of it like sorting animals. A dog and a fish are both animals, but they behave very differently. In the same way, a linear function and a quadratic function are both functions, but they grow in completely different patterns. Why do we bother sorting functions into types? Because knowing the type tells you how something will behave. If a car's speed grows linearly, it gains the same amount each second. If it grows quadratically, it gains more and more each second. That's a huge difference. In calculus, we'll learn to find the rate of change of a function, and the rule for that rate depends completely on the function's type. The derivative of a linear function is just a constant, but the derivative of a quadratic is another function. So spotting the type early is like knowing whether you're dealing with a bicycle or a rocket. It tells you what to expect and which tools to use. Let's look at the main types you'll meet in this course. A linear function has the rule f of x equals mx plus b. Its graph is always a straight line, and it grows by the same amount m for every step in x. We call m the slope. A quadratic function has an x squared term. Its graph is a u-shaped curve called a parabola. If the x squared coefficient is positive, it smiles. If negative, it frowns. A polynomial is just a sum of power terms like x cubed, x squared, x, and a constant. Linear and quadratic are special cases. A rational function is a fraction where the numerator and denominator are both polynomials, like 1 over x. That one has a break at x equals 0 because you can't divide by 0, the domain excludes it. Let's solve a real problem. A taxi charges a base fare of 50 rupees plus 20 rupees for every kilometer you travel. The total fare depends on the distance. This is a linear function because the cost grows by the same 20 rupees for each extra kilometer. We can write the rule as f of k equals 20k plus 50, where k is the distance in kilometers. The 20 is the slope, the constant rate of change. The 50 is the starting value when k is 0, called the y-intercept. Now, if you ride for 8 kilometers, just plug in k equals 8. 20 times 8 is 160, plus 50 gives 210 rupees. That's your fare. This same method works for any linear relationship, a phone bill, a car traveling at steady speed, or a water tank filling at a constant rate. A function is a rule that takes an input x and gives an output f of x. We can write it as a formula, but a graph turns that rule into a picture. It plots every input-output pair as a point on a flat surface, with the input along the horizontal axis and the output up the vertical axis. Reading a graph means looking at the picture and answering two kinds of questions. For a given x, how high is the point? That is finding f of x. And for a given height, what x values land there? That is solving f of x equals some number. Transforming a graph means taking that whole picture and moving it, stretching it, or flipping it, to get the graph of a new, related function. It is like picking up a drawing on a sheet of paper and sliding it around, or pulling its edges to make it taller or wider. In calculus, we are always asking how a function changes. Does it go up or down? How fast? Where does it turn around? A graph answers these questions at a glance. The steepness of the curve is the rate of change, which is exactly what the derivative measures. The area under the curve is what the integral measures. So reading a graph is like learning to read a map before you go on a journey. Transformations matter because they let us understand complicated functions by relating them to simple ones we already know. If you know the graph of x squared, you can instantly draw the graph of x squared plus 3, or 2 times x squared, just by shifting or stretching the picture. This skill turns a handful of basic graphs into a whole library of functions, which is essential for solving calculus problems quickly. Let us build these transformations from the ground up. Think of the graph as a set of points where the y-coordinate is exactly f of x. If we make a new function g of x equals f of x plus k, then for every x, the output is k units higher. So every point on the graph moves straight up by k. That is a vertical shift. If we subtract a positive number h inside the function, writing f of x minus h, something interesting happens. To get the same output as before, x must be h units larger. So the whole graph slides to the right by h. It feels backwards, but the reason is that the input needs to be bigger to compensate for the subtraction. For stretching, multiplying the whole function by a number greater than 1 pulls every point away from the x-axis, making the graph taller. Imagine standing on a 20-meter cliff and throwing a ball straight up. Physics tells us its height after t seconds is h of t equals negative 5t squared plus 20. This is just the basic parabola negative 5t squared, which opens downward, shifted up by 20 meters. Let us read the graph to find when the ball is 10 meters above the ground. We look for the points on the graph where the height is 10. Setting h of t equal to 10 gives negative 5t squared plus 20 equals 10. Subtract 20 from both sides, negative 5t squared equals negative 10. Divide by negative 5, t squared equals 2. Taking the positive square root, since time is positive, t equals root 2 seconds. Root 2 is about 1.4. So the ball passes 10 meters on the way up at about 1.4 seconds. Imagine folding a graph along the y-axis. If the two halves match perfectly, like a butterfly's wings, we call the function even. Now, instead of folding, imagine spinning the graph halfway around the origin, like turning a steering wheel 180 degrees. If it lands exactly on top of itself, we call the function odd. These are just two special kinds of symmetry a graph can have. An even function gives the same output for a number and it's negative, like f of 3 equals f of negative 3. An odd function gives the opposite output, so f of negative 3 equals negative f of 3. Why do we care if a function is even or odd? It's a huge shortcut. If you know a function is even, you only need to figure out half its graph, the other half is just a reflection. This saves time when you're sketching complex functions. More importantly, in calculus, symmetry can make tough problems disappear. For example, finding the area under an odd function from -a to a always gives 0, because the positive and negative parts cancel out perfectly. Recognizing this instantly can turn a long calculation into a single line. It's like knowing a secret passage in a maze. So how do we figure out if a function is even or odd without a graph? We test it with algebra. Take the function and replace every x with a -x. Then, simplify. If you get the exact original function back, it's even. If you get the exact negative of the original function, it's odd. A quick trick for polynomials is to look at the powers. Even functions are built from only even powers of x, like x squared or x to the fourth. Odd functions are built from only odd powers, like x cubed. But watch out, most functions, like x squared plus x, are a mix and are neither even nor odd. They have no special symmetry. Let's test this with a real example. Suppose we have the function f of x equals x to the fourth power minus 7x squared. To check if it's even, we find f of -x. We replace each x with -x, giving us -x to the fourth power minus 7 times -x squared. A negative number raised to an even power becomes positive, so -x to the fourth is just x to the fourth, and -x squared is x squared. This simplifies to x to the fourth minus 7x squared, which is exactly our original function, f of x. The test works, so this function is even. Its graph will be a perfect mirror image across the y-axis. A periodic function is one that repeats its values in a regular pattern. Think of a clock's minute hand. Every 60 minutes, it's back at the same position. In math, if you shift the input by a certain amount, called the period, the output doesn't change. We write this as f of x plus t equals f of x, where t is the period. The smallest positive t that works is the fundamental period. So, a periodic function is just a function that cycles over and over, like a heartbeat or the seasons. Why do we care about repeating patterns? Because the world is full of cycles. A swing goes back and forth, a guitar string vibrates, the sun rises and sets. If we can describe these with a function, we can predict what happens next. For example, knowing a Ferris wheel's period tells you exactly when you'll be at the top again. In calculus, periodic functions are the gateway to trigonometry, which lets us model waves, sound, and light. So, periodic functions turn a repeating pattern into a tool we can analyze and use. Let's build a periodic function from something you already know, a circle. Imagine a point moving around a circle at a steady speed. Its height above the center goes up and down, repeating every full turn. If we plot that height against time, we get a wave. The time for one full turn is the period, t. On a graph, you can see the pattern repeat. Pick any point, move t units to the right, and the graph looks exactly the same. The simplest periodic functions are sine and cosine, which come directly from this circle idea. Their period is 2 pi, because a circle has 2 pi radians in a full turn. So, a periodic function is just a rule that cycles its output, and its graph is a repeating wave. Let's solve a real problem. A Ferris wheel has a radius of 10 meters and its lowest point is 2 meters above the ground. It takes 4 minutes to complete one full turn. We want a function for your height above the ground over time. The height goes up and down like a sine wave. The period is 4 minutes, so the function inside the sine must have a factor that makes it repeat every 4 minutes. That factor is pi over 2, because sine of pi over 2 times t completes a full cycle when t goes from 0 to 4. The sine part gives values from -1 to 1, so we multiply by the radius, 10, to get the height variation. We add 12 to shift the center up, since the wheel center is 12 meters high. So the height function is 10 times sine of pi over 2t plus 12. Let's find your height at 1 minute. A composite function is simply one function plugged into another. Imagine you have two machines. The first machine, G, takes your raw number x and does something to it, like adding 3. Its output, G of x, then goes straight into a second machine, F, which might square its input. So the final output is f of g of x. We write this as f of g of x, or with a little open circle, f composed with g of x. It's a two-step process where the output of the inner function becomes the input of the outer function. Why do we care about chaining functions together? Because the real world rarely changes in just one simple step. Think of a balloon being inflated. The pump increases the radius of the balloon over time, so radius is a function of time. But what you actually see is the volume growing. Volume is a function of radius. So the volume over time is a composite function. You plug the radius function into the volume function. This idea of chaining rates of change is exactly what leads to the chain rule in calculus, one of the most powerful tools for understanding how things change. It lets us break down a complicated change into simple, understandable parts. To evaluate a composite function, you always work from the inside out. Take a number x, find g of x first, then feed that result into f. The domain of the composite is trickier than a single function. It's not just the domain of the outer function. The number x must first be a valid input for the inner function g. Then, the output g of x must be a valid input for the outer function f. So the domain is all real x that survive both checks. A common mistake is to think f of g of x is the same as g of f of x. They are usually completely different. For example, if f squares and g adds 3, f of g of 2 is 25, but g of f of 2 is 7. Order matters. Let's solve a concrete everyday problem. A store is having a sale, 20% off everything, but then you have to pay an 8% sales tax on the discounted price. You have $100. What do you actually pay? The discount is applied first, so that's our inner function. 20% off means you pay 80% of the original price. So g of x is 0.8x. Then the tax is applied to the discounted price. An 8% tax means you pay 108% of the discounted price. So the outer function f of x is 1.08x. The composite function is f of g of x, which is 1.08 times 0.8x, or 0.86 for x. For a $100 item, the final price is 0.86 for times 100, which is $86.40. Imagine you have a machine that takes a number, doubles it, and adds 3. You put in 2, and out comes 7. An inverse function is like a magical rewind button for that machine. You feed the output, 7, back into the inverse machine, and it perfectly recovers the original input, 2. Mathematically, if a function f takes an input x and gives an output y, its inverse, written as f inverse of y, takes that y and gives you back the x. It simply swaps the roles of input and output. The little -1 in the notation is not an exponent, it's just the symbol we use for the inverse. Why do we need this rewind button? Because in real life, we often know the result but need to find the starting cause. For example, if you know your final exam score after a curve was applied, you might want to know your raw score. In calculus, many powerful functions like exponentials, logarithms, and trigonometric functions come in pairs that undo each other. To solve an equation like e to the power of x equals 5, you need the inverse function, the natural log, to extract that x. Without inverses, we'd be stuck. They are the master key for unlocking unknown inputs from known outputs, which is exactly what solving an equation means. To find an inverse, we follow a simple recipe. Start with your function, like f of x equals 2x plus 3, and write it as y equals 2x plus 3. The core idea is to swap the input and output, so rewrite it as x equals 2y plus 3. Now, solve for the new y, subtract 3 from both sides to get x minus 3 equals 2y, and then divide by 2. So y equals x minus 3 over 2. That new expression is your inverse function, f inverse of x. Visually, a function and its inverse are perfect mirror images of each other across the line y equals x. If a point A, B is on the original graph, then B, A is on the inverse graph. Let's use this in a real situation. You're traveling and see a weather report of 86 degrees Fahrenheit, but you only understand Celsius. The conversion formula from Celsius to Fahrenheit is F equals 9/5 C plus 32. We know the output, F, is 86, and need the input, C. This is a perfect job for the inverse function. We swap the roles, start with F equals 9/5 C plus 32, and solve for C. Subtract 32 from both sides, F minus 32 equals 9/5 C. Then multiply both sides by 5/9. So C equals 5/9 times F minus 32. Plug in 86 for F, 86 minus 32 is 54. Then 5/9 times 54 is exactly 30. So 86 degrees Fahrenheit is a warm 30 degrees Celsius. The inverse function. Let us rewind the conversion.